Let's do a numerical based on the masses suspended by a frictionless pulley. So we have the picture given as follows. The two masses are given to be in motion, and what we are required to find is acceleration A of the masses and the string. So as we can expect in this pulley system, the mass m would be moving downwards. So we have to find with what acceleration it is moving down. And the same acceleration will also be applicable for the other mass in the opposite direction. And of course, with the same acceleration, the string will also be on the right-hand side, it will move down, and the string on the left-hand side will move up. Then we have to find the tension T in the string. So since there is a weight acting downwards, there will be a tension T on the right hand side, and there will be a same amount of tension T on the left hand side. So we have to find the value for that tension and F net on M. So with respect to M, there are two forces acting. One which is the weight of the object in the downward direction, and there is a tension T in the upward direction. So we have to find what is the net force or resultant force which is acting on both the masses. So F net on both the masses. And then finally, we have to draw the free body diagram for M and M. So let's proceed. Also, one very important thing, as far as the theoretical concepts which are required to solve this numerical, I have prepared another video, masses suspended by a frictionless pulley. So it'll be good if you have a look at that because we are going to use those theoretical concepts in this numerical. So let's calculate first the acceleration A of the masses. So as I have shown in my previous video, I have done the derivation for the acceleration, which is acceleration equals to the difference of the masses divided by the sum of the masses times g, acceleration due to gravity. So we simply put in the values that are given. The bigger mass is 10 kg minus smaller mass 5 kg, and then divided by the sum of the masses times g. So a very simple calculation. So this is 5 over 15 times g, which is nothing but g over 3. So of course, the units will be meter per second square, it being acceleration. Now, very important point to understand, and as I have also explained in my previous video, highlighted below, the acceleration of the small mass will be equal to the acceleration of the bigger mass. We are talking about the magnitudes of the acceleration, and that will also be the acceleration of the string. Now in the string also, we see that there is a left-hand side of the string, and then there is a right-hand side of the string. So if I say the entire system, if I represent it as the string and the two masses, the entire system is moving with the same acceleration. So acceleration of the left-hand side of the string has to be equal to the acceleration of the right-hand side of the string. And therefore, all of them have the same value, g over 3 meter per second square. Now, one very important thing to understand over here is that in such questions, the value of the acceleration will always be less than the value of acceleration due to gravity, which means it will always be less than 10 meter per second square. So what is the reason for that? I've also explained in that video, but in short, since this is given as m minus m, which is the difference of the masses times over m plus m, which is the sum of the masses times g. If you see the numerator, the difference will always be lower than the sum of the two masses, and therefore it will always be less than g. Now, as far as the direction of the acceleration is concerned, the bigger mass will be moving vertically down. So the acceleration will be pointing down, and the smaller mass will be moving up, and therefore the acceleration of the smaller mass will be pointing up. So the magnitudes of the acceleration of the two masses are the same, but the directions are opposite. And the same applies for the magnitude of the acceleration of the string on both the sides is the same, and the direction is opposite. Now, let's calculate the part B, the tension T in the string. And as I have shown in my previous video, the tension is given by twice the product of the two masses over the sum of the two masses times G. So if we put the values, it's very easy to see that it will be given as 100 over 15G, which is actually 20 over 3G. It's also important to understand that the tension on the left-hand side of the string will be equal to the tension on the right-hand side of the string, and therefore I represented them with a common letter T. And now coming to the value, what's the significance of this value? First of all, the unit will be unit of tension is force, and therefore it has units of Newton. So now it's very important to analyze the value of the tension that we have got, and important to remember that the value of the tension should be, as I explained in my video highlighted at the bottom, should be less than the weight of the bigger object, and it should be greater than the weight of the smaller object. Let's see whether it satisfies in our question. This is our value is 20 over 3G. That's the value of tension. Let's see if it is less than mg. So m is 10, so this becomes 10G, and the smaller mass is 5, so therefore this becomes 5G. So 20 over 3 is 6.67 G. It is definitely less than 10G, and definitely it is also greater than 5G. So you should be able to kind of get a verification whether the value that you got is within the limits that is expected. So with this, we have the confirmation that the value of tension is less than the weight of the bigger mass and more than the weight of the smaller mass. Now let's focus on the very important part of this question, which is draw the free body diagram for both the objects. So what's a free body diagram? It's basically all the forces that act on that particular object which we are talking about. So let's say if I take the bigger object as the first object, I have to see all the forces that are acting on that object. The first force that we see is the weight of that object, and then weight is acting vertically down, and then there is a force of tension T in the string, and we have derived the value earlier, which is 20 over 3 times G. It's also important, I have drawn proportion to the scale. If you see very carefully, I have drawn the weight of the object bigger in magnitude as compared to the tension. So if you see the weight, this is 10G, and it is higher than the tension. Now, even though it is higher, we still need to be able to arrive at the number. So what is F net? So F net is actually the net force. So if you do the resultant of the two forces, it will be pointing downward, as this picture shows. And what's the value of that? So that will be the weight minus the tension. Yeah, so downward force is, I have taken downward direction as positive, therefore the weight will be positive, minus because tension is acting vertically up, which is a negative direction for me. So if I put the values, this will be 10G minus 20G over 3, which is 10G over 3. That's the net force acting on the bigger object. Now let's do the similar free body diagram for the smaller object. So for the smaller object mass m, let's see what are the forces. So the weight of the object acting vertically down, and the tension T, which is acting vertically up, and we have in the previous section seen the value of the tension is 20G over 3. So I've drawn these vector diagrams proportional in a scale, which means since the object is moving up, therefore the tension has to be bigger in magnitude as compared to the weight. And how much is that magnitude? So that is again given by this formula. Net force on the object M will be tension T, because this time I've taken the direction of motion as upward as positive. So force of tension T will be represented with a plus sign, minus G, because weight is acting vertically down, which is opposite to the direction of motion, which I consider as positive. So if you do this mathematics, this will be 20g over 3 minus 5g, and therefore the net force is 5g over 3. To summarize, on the right hand side, since the weight is higher than the tension, so there is a net force in the downward direction. And on the left hand side, since the tension is higher than the weight, therefore the net force will be in the upward direction. The two forces are not equal in magnitude, as we clearly see. The force on the net force on the right hand side is twice the force on the net force on the left hand side, and the factor is 2, as we have seen in the previous section, and the two forces are acting in the opposite direction.